Can I?
Actually, the slide of silence I really like this. I really take the view on the
Yeah, good afternoon. Welcome back after lunch. I hope you enjoyed the sandwiches. My name is Werner Adenauer. I'm from the Johannes Kepler University in Linz, Austria. And I will chair the first technical session of the circle workshop on molecular communications for microfluidic networks. We will have 5 very interesting talks. And we will start with Professor Morabito, which is from the University of Catania, which will present us the research output of the last 5 years, or around 5 years, for microfluidic communications and networking. His group was, let's say, the first one in 2012, which came up with this idea of using microfluidics for communications and for networking.
Okay, thank you very much for, thanks a lot. Thank you very much for giving me the opportunity to present our work in this domain we have been carrying out. Okay, so the title will be From Microfluidic Communications to Microfluidic Networking, but I still haven't found what I'm looking for, which is a track by U2. It's a song in the Joshua Tree. It was recorded 200 meters from here, so this is the reason for this title. So let's start by spending a few words about microfluidics. Microfluidics refers to the study and development of systems that manipulate small amounts of fluids running into channels in microscales. Usually they are built using plastic or glass. Okay, you can distinguish 2 different domains in the microfluidics. So you will have continuous microfluidics and discrete microfluidics. In the case of continuous microfluidics, basically you have that there will be just one type of fluid flowing through the microchannels. And there have been quite some work already also in this domain, because there has been, especially in the molecular communication context, there are some references here. We will talk, however, about discrete microfluidics. In discrete microfluidics, basically, you have 2 different fluids, or more than several fluids flowing through the microchannels. You can distinguish droplets, in fact, that you can call dispersed phase, that will be carried by another immiscible fluid called continuous phase. And therefore, these droplets will run through the microchannels. Droplets are a fantastic environment to execute laboratory processes, because they basically provide an isolated environment. So you can have different droplets, and in each of those droplets you can perform a specific microbiological process, okay? And they have been studied a lot. So some time ago we ran into this paper. It was published in 2007 by Prakash and Gershfeld in Science, and the paper was about designing logic gates by exploiting just microfluidic phenomena. So it's great, because by using this approach you can build microfluidic computing systems, okay? But then if you have computing, our question was, why not communications, okay? But before investing our time in this domain, we decided to run through a reality check about this idea. And this reality check was mostly giving answer to 3 simple questions. The first one is the most obvious. Does it make sense? Okay. So we went through the literature, and we found that there was a paper published in Science in 2007 again, which was envisioning something like a sort of encoding and communication in the microfluidic domain, discrete microfluidic domain. So we said, okay, there is other people talking about that. They gave credit to them, so it makes sense. First question, check. Second question, do we have the required background to run research in this domain? We are ECE, right? We are engineers, electrical and computer engineering. So can we work in this domain? So again, we studied a little bit, and we found that there is this fantastic Hagen-Poiseuille law of microfluidics, which is basically the same as the Ohm law. So you can study microfluidic systems like electrical circuits. So great, we can study that. We just need to know that droplets will create an increased hydrodynamic resistance, and that droplets, when they arrive at the bifurcation point, they will always choose the branch with the minimum hydrodynamic resistance. So at that time, our simplistic way of seeing microfluidic system was that one, but we said, okay, we can handle that. We can go ahead. Third question, do we have the commodities to run research into the microfluidic domain? So what is the software that is needed? And we saw that the most popular software for studying this type of systems are the COMSOL and OpenFOAM. COMSOL is a commercial software tool. Gianluca spent a few words about it before. It's quite expensive, but it turns out that in our department we have a few licenses, so it's fine. The other one is OpenFOAM, which is open source, so no problem with that. But if we want to go beyond just simulation and we want to see things actually working, what do we need? How can we create prototypes? And we saw that there are some simple ways that can be used in order to create prototypes of microfluidics chips. And some are based on the use of some cutters. I mean, I cannot go into the details. We have small amount of time, but there are possibilities to do that. The most simple way to do it is by exploiting 3D printers, okay? So it's possible to create microfluidic channels in that way. We measured the performance of such channels, so if you are interested in more details, you can go through that paper. Now, we can create prototype. What do we need to test them? Well, this is a picture of our microfluidic equipment laboratory. It's, you know, it's worth 1,600 euros, everything included, and 93% is just the pumps, okay? All the rest will be an Arduino card and some recycled material that this guy took from broken TV sets and all the lamps and this kind of. This is basically, you know, the lamp of Pixar, you know, it just cut it. I mean, you can build a laboratory with a very small amount of money. So great. We can start working on that. So we needed a vision, and our vision was this one, okay? It was what we can call the networked labs on a chip. What is a networked lab on a chip? A lab on a chip is a system that you can put in a chip that can execute laboratory operations. Usually, those labs on a chip are very vertical, which means that they are designed and they can execute just one type of application. We would like to have them programmable. Okay? And in order to do that, we thought that the possible structure could be something like that. You have different modules in your chip, and each module is specialized in executing a given biochemical function. And in this way, if you want to create a complex biochemical process, you can send your sample through a given sequence of such elements. Now, the nice thing at this point is that you will need to route droplets through your microfluidic network, which is basically the work that networking people is doing since 40 years, right? So it is our job. So we needed to work on that, and we said, okay, the first thing we need to do is encoding information. How can we encode information in a droplet microfluidic system? We studied two different options, basically. One uses the presence-absence encoding. I will spend a few words about that. The other, distance encoding. Presence-absence encoding means that you logically divide the time in slots, and then it's simple. A droplet in one slot means 1, no droplet in that slot means 0, okay? So very simple. The distance encoding is a little bit more complex, even if also in that case quite simplistic, because you have that your information can be encoded in the distance between consecutive droplets, okay? They are quite obvious techniques. We calculated the capacity of such approaches and made a comparison, trying to finding out when it's more convenient, the one and when the other. Obviously, there are other options beyond those that we have studied. You could encode information in the size of the droplet. Andrea Zanella's group is working on that. Or you could do it in the composition of the droplets, in the chemical composition that you have inside the droplets. Or you could work in a combination of those approaches. But anyhow, we had encoding. The other step needed was switching, because we want to route droplets inside the system. So we need to build an element which is able to switch droplets toward one direction or the other. And we wanted to do it passively. We wanted a passive element, not active element. So what we thought is to create what we called microfluidic packet. A microfluidic packet is composed by an header droplets and the payload droplets. The payload droplet will contain the sample that you want to process, whereas the header droplets will be used just for signaling purposes. And basically what you will do is that you will encode the address of the destination element when you want to send where you want to send your droplets inside the distance between the header and payload droplets. So this was the idea. Therefore, what we need to do is to create a structure that will steer droplets depending on their mutual distance. And this is the simple structure that we thought. Basically, it's here. You have that your droplet will arrive through this channel, and when they arrive at this bifurcation point, they will need to decide whether to go on one side or the other side. The first droplet, the other droplet, will always go towards the bottom. Why? Because there is lower distance. Okay, the distance, lower resistance. Because the resistance is lowest here in this channel. We designed it in this way. When the second droplet arrives at this bifurcation point, this is the payload droplets, the directions that it will take will depend on the position of the other droplets. In fact, if the other droplets is still here, okay, the payload droplets will decide to go towards upwards, okay, because there will be lower resistance. Droplets will put additional resistance there, okay? Otherwise, it will follow the other droplets. In this way, what we can do is that by modulating the distance between these two droplets, we can steer the payload droplets as desired. We ran our simulation and we built a prototype of it, okay? And actually it worked. This is a picture with just one, but actually we have a cascade of two of those elements, and it worked as expected. If you want more details, obviously there are papers about that. So we have a switch. We can think to build a network, okay? So this is the structure of the network we thought. So we have one master. This will be the active part of the system. And then you will have several slaves. Each of those slaves will perform a specific biochemical function. So what you need to do is that the master will send the droplets inside the request bus. At a certain point, the payload droplets will go towards one of those elements, and then it will arrive again in this other bus that we call the response bus, and go again to the master that will decide on the next step, okay? So this is basically the idea. We have already the switching part, I explained it before. We needed something here to regulate access to the response bus, because we might have here collisions. So what do we need? We are telecommunication networking people. We need the medium access control. And we implemented this using this structure, which is quite simple also in this case. Basically, you have the droplets is coming from your slave, and it wants to arrive into the response bus. But when it arrives here, we call this trapping zone. Basically, if there is a droplet inside this area, it will remain stuck here. It will not be able to go ahead. This is because the droplet here will divert will be such that the flow will go like this and will keep the droplet stuck in this area. When the droplet that is in the response bus, in this thing that we call the sensing zone, will leave the sensing zone, the conditions will get back to their original status, and then the droplets can go towards the response bus. Again, further details can be found in this paper. But now let's go to the title of my talk, that is, but I still haven't found what I'm looking for. What is that I'm still looking for? It's an answer to a simple question. And this is the question that basically Alfio Lombardo is the guy that we work together, and I, when we go in our small boat, okay, we end up asking us, why are we doing all this stuff, okay? So in the beginning we'll say, what's next? That was great, okay, what should we do next? Encoding, then switching, then medium access control. But now the question becomes, why are we doing that, okay? What is the application? Taking into account that labs on chips are much more specialized, much more vertical than we originally thought. This is the first thing. Second thing, usually the biochemical processes we have seen discussing with people just envision 2 or 3 steps. So no large sequences or long sequences of processes in the same sample. Third, most of the problems that we addressed are mechanical problems. So why telecommunication people, like we are, should take care of those issues? So basically, what we need is a killer application that involves the transfer of digital information. So this is what we are looking for. We didn't find anything for a long time. We have just one idea we're exploring right now that I will share with you. So this is a chart by, it's a market forecast by IDC that gives you an idea of the explosion of what is called the digital universe, which is the amount of data which is generated yearly. So you can see that this red line is exploding, is going very, very up, okay? On the other side, the green, where is that? The blue one is the amount of storage which is currently available. So obviously you don't need to store all of this data, you will store just a portion of it, okay? But it's clear that the system will collapse. It's just a matter of a few years. At a certain point you will produce more data than your storage can afford to store. So you need a solution. People have been working on that, taking into account that the density of the current technologies, tapes and optical disks are large but not that large, and that you need to replace them each 10 to 30 years. 10 to 30 years might seem a long time, but when you have to run a huge infrastructure and you have to recreate it each 10 to 30 years, it becomes very problematic. So, people, it's not our idea, have proposed to use DNA for this reason. So you can encode information into DNA. It gives you 10 to the 9 gigabytes per millimeter cube, which is 7 orders of magnitude higher than optical disks. And it will retain the data for 500 to 1,000 years, right? Because you can see the DNA of a mammoth right now, okay? Then the animal was that long time ago. Okay, so now this is not our idea, as I told you. What can we do? What can we do is to use microfluidic for cabling those type of systems. Let me explain. There are people that have proposed what they called DNA-based archival storage systems, okay? Droplets and microfluidic can be used in order to move such information from one part of your system to the other. Okay, so our concept is the following. Here you have all the modules needed in order to encode information. Then you will create your droplets, okay? And then you will need to store the droplets inside the DNA storing information in what we could call sectors. You know, in the hard drive you had sectors. You you have to write in a given hard drive sector. And in microfluidics, you can do it by using some microfluidic traps or microfluidic pools. So basically, you will have that your droplets, if you want to send the droplets towards a given sector, you will need to switch the droplets in such a way that it will reach the pool P2. So this is basically the idea. If you want to read it, you will send an empty droplet to the same pool. When the droplets arrive here, it will push this droplet out, and so it will go to the reading components. This is what we have been thinking of. Is it the answer? Is it the killer application? We don't know, right? But we enjoy doing that, so we will keep working on this domain. If you have questions, I will be more than happy to answer. Thank you.
Thank you for this very interesting talk. Are there any questions from the audience?
Thanks a lot, Giacomo. Very interesting. Just two very short questions. One is, can you cope with some amount of asynchronicity in your network, or you need a global synchronization?
Our network is asynchronous.
It's asynchronous.
Yeah, because we use distance encoding. Okay, you said when I discussed about encoding, I told about two different approaches. One was presence-absence. In that case, you need synchronization. We are asynchronous. Then what happens is that we encode information in the distance. The microfluidic channels might modify such distance, but this is sort of noise. So this is the way in which we deal with it.
That will allow scalability, right?
Yeah.
And then the second question might be premature, I understand you're still looking for.
Yeah.
Not yet. But can you at least speculate on reliability and reproducibility of this very last ideas?
Okay. We have just a couple of simulation here. This is very new. The paper is under review right now. It's for a conference, so it's not even that big. So the issue here is that we are completely unaware of those. We know that it's possible to do that, okay, but we don't have know-how to do that. So right now we are looking for partners, okay, in order to make something reasonable in that domain. This is my question. My doubt right now, we are discussing, fighting between ourselves, is whether we need to do that passively, or it's worth it to do it with active electrowetting, I mean, with techniques that can be used and would be much more comfortable, let's say. But I think that at the end we will finish with a mixed approach in which you have a sort of distribution which is performed through electrowetting, and then the final branches, the leaves, will be dealt with in a passive way. This is my guess, but it's, you know, what I'm thinking right now. I don't know whether we will end up with this or not. So we are still studying on that. Yeah.
Very naive question.
Very naive response.
Okay, good. So everything is based on these droplets, and the droplets that actually are the carriers of your signals, and how you organize your droplets that allows you to process them like digital circuits. Right?
Okay, so...
Yeah? That's understood. Okay, so understood properly what you're talking about. Aren't you trying to force something new in an old framework? In the sense that you want to change technology, you want to look at novel forms of communication, novel forms of information processing via those systems, but you force those novel ideas of droplets into a very rigid structural framework that has to meet like synchronous clocks, and they have to go in and have to wait and then have to go out and have to no collisions. I mean, do you not simply have to look at a different architecture for doing more advanced things with this kind of technology and to arrive at your killer application? Okay. Does that make sense at all, what I'm talking about here?
Yeah, I totally understand. Actually, you know, you have a very good point about that, because maybe it's our our attitude, which is wrong in the very beginning, because we said, okay, we want to bring our know-how and our background in this domain. You are saying maybe this is not the right attitude, right? Maybe you would say, okay, this is a new domain. You can think that communication and networking would be interesting there. Why don't you think to a totally different approach? Good question. I will take as homework, right? Nice.
The simple idea would be two droplets meeting and making a bigger droplet.
Yeah, this is.
And then separating again in smaller droplets. I mean,
I see what.
I mean, so you have other ways of doing information processing, but you don't really use them. You turn it back to the simply 0-1 bits in the right location, like we know.
Yes. Actually, there is in some cases we consider that possibility, but in any case we were not considering it as an opportunity. So this is your point. So this is a new opportunity to think to something totally different.
Because like you say, I now know how it works. Now we know we have done that. We have done all the schemes. Let's go beyond and let's forget about this and make it.
Yeah. But okay. But I have a different, an interesting story. Maybe I can talk to you afterwards about that. But it's even difficult to have people in our community to accept this traditional approach. If we change, even also the approach, it might be very, very difficult. Really, very, very difficult. So I totally, you have a good point. I will take it as homework, as I told you. Thank you very much.
Just a very short question.
What would you say the fundamental limits are of this approach? So it's related to you, but more succinctly, what are the fundamental limits of these kind of devices in the context of communications?
Okay, the fundamental limits are basically due to the fact that these are not linear systems, and you cannot study those in an isolated way. Okay, we are used to system in which we put two together, okay, and they will work independently one from the other. In this case, no, everything is very connected with each other, and this is something that we need to work it from, it's just a problem of architectures, most probably. There is also a physical limit that is due to the fact that the bigger becomes your network, the higher becomes the difference of pressure, the pressure that you need to inject into those systems. Just the pressure itself, fluid, and this is a problem because you will need lots of energy, lots of pumps that are very precise, even when they need to be very strong, let's say.
So effectively, this might have some kind of analogy to water distribution networks, right? So, for example.
Yeah.
Okay.
Yes.
So you might have like phase transitions and maybe even leakages.
Yeah. But as I told you, most probably, okay, we were like pure hydrodynamic. Most probably the right approach is a mixture of active droplet steering, like electrowetting is a possibility, and purely hydrodynamic, in order that you can get, the right trade-off between the two approaches. This is my guess.
Any other questions? I have one short final question to your last slide.
I don't think right?
For reading,
Okay.
previous slide. For reading the stored DNA, you said you send an empty droplet, push DNA.
So you send the empty droplet here, you push it here,
and
it arrives here, you create a copy.
When you have to,
then you send this here, and this will go.
The question is on the pushing. So how do you prevent this?
It happens. One droplet will push the other. It's something that happens. No, they will not coalition. There will not be coalitions. And then you will have, you will reestablish the initial.
So how can you prevent these collisions?
Sorry?
How do you prevent these collisions?
It just happens. Okay. I don't know why.
Okay.
I'm not into these microfluidic details, but it's a structure.
It's possible.
Yeah, we didn't invent it. Okay, it just is like that. Okay. Yeah. In certain conditions, at least.
Okay. Thanks a lot again.
Thank you very much.
next speaker is Professor Andrea Zanella from University of Padua in Italy, and he will give more details on how microfluidics can be used for communications purpose, including also experimental results, if I'm informed correctly. You need the microphone or?
Well, maybe. Does it work? All right. Okay. Thank you. So, sorry. What is going on here? I should disable the Wi-Fi. All right. So, good afternoon. My name is Andrea Zanella from the University of Padua, again, in Italy. And this talk is somehow connected to the one of my colleague, Morabito, who actually introduced me to this domain. So I have to thank him, maybe, I don't know. So the typical outline of a talk like this starts with an introduction to microfluidic that, however, I'll skip since Giacomo has already done the work for me. And then I'll focus on our specific contribution on this domain, presenting some of very preliminary experimental results we obtain in our lab. So as you could guess from the previous presentation, the research in this domain can take two different directions. In one case, you can study microfluidic networking, that is the combination of these microfluidic devices to carry droplets where you want in a complex circuit. Another approach instead is the one that I call microfluidic communication system, where you try to transmit bits as standard communication systems, but using these microfluidic things as carriers. All right? So the previous talk was mainly on this domain, while this talk will be on the second one. So what I describe here is a very, again, preliminary study that was aimed at investigating the possibility of delivering bits by using these droplets as carrier of our information. So what we did was designing, again, a very basic pulse amplitude modulation type of modulation, and where we used the droplet size or the distance between droplets in a train of droplets to carry our bits of information. Why? Because it was simple. The first approach that came to our minds when we were thinking a way to communicate bits using this technology was this one. So we just we performed some experiments in our lab, and then we made some considerations that I'll explain the next minute. So to begin with, in order to send bits using this microfluidic technology, we need to create the droplets, right? That are our information carriers. So the mechanism that we use to create droplets, there are many different mechanisms in the microfluidic domain, but the simplest one probably is this one, where you have one main channel filled with a fluid that is called continuous phase, and it behaves as the carrier. And then you have a second channel that intersects the first one, where you pump in a second fluid. Under certain conditions that we'll discuss in a minute, this second fluid will be dispersed in the form of droplets. So here you can see some of the notation that will be used later on, but the more important, let's say, parameters are these two terms here, QD and QC, that represent the volumetric flow rates of the dispersed phase, so the fluid that gives rise to the droplets, and of the continuous phase, that is the carrier. So actually, the formation of these droplets is not a process that always happens, but it depends on what is called the capillary number. That is a number that captures the relative magnitude of viscous forces and other forces, interferential tension forces. So if this number is above a certain threshold, then you don't have really droplets, but what you have is something like this. The two flows will flow together in parallel streams in your channel, and this region is called drippling region. Instead, if the capillary number is small, then you enter what is called the squeezing region, where you have this droplet formation. Why is it important? Because you can see that the capillary number depends on a number of factors, but is proportional to the volumetric flow rate of the carrier fluid. What does it mean? It means that we cannot pump the carrier fluid at a very high speed, because otherwise we will not observe any longer the formation of droplets. We will switch from this regime to the other one, all right? So we have a limit on the maximum speed, let's say, of the continuous carrier, of the continuous phase. If we are in the squeezing regime instead, we can observe the formation of droplets in a very regular and kind of deterministic pattern. This is small clips that we recorded in our lab. When I say our lab, I don't mean my lab. Actually, it's a lab in the physics department that collaborated with us for these experiments. So you can see the formation of droplet. Well, here the speed of the, well, first of all, the size, of course, has been zoomed in a lot, and the speed has been slowed down a bit. But you can see that the droplets are formed in a very regular pattern, in a very regular manner. And actually, in using this T-junction to create the droplets, you can also control the size of the droplet by playing with these two parameters. So the volumetric flow rate of the continuous phase, QC, and of the dispersed phase, QD. So if you keep the continuous phase with a constant flow rate, and you increase the rate of the dispersed phase, so you basically pump more fluid into the channel in the unit time, what you get is that the droplets become progressively longer and longer. Okay? That's pretty intuitive. However, since you have to conserve the mass of your fluids, if you increase the length of the droplet without changing the volumetric flow rate of the continuous phase, the distance between droplets will be reduced. So you can control the droplet length of the distance between droplets playing with these two parameters, but not independently. So you either control one and the other one is given, or vice versa. So how can we modulate, therefore, these physical things in order to carry information? So we started with, as I said, the basic modulation. So we consider a 4-symbol constellation with 2 bits per symbol. Each of these combination of bits is assigned to a different symbol, number from 0 to 3. And then we assume that each symbol can be represented by droplets of different lengths, as in this case, or maybe by different interdrop distances, either one or the other, because, as I said, you cannot control one without affecting the other. In order to obtain these 4 different lengths of droplets, we can keep the volumetric flow rate of the continuous phase constant and change the speed of the dispersed phase. So we increase the speed from 0.5 to 2 with a step of 0.5 microliter per minute. And doing that, we could obtain droplets of different lengths, from the longest to the shortest. Why have we decided to opt for a 0.5 increase? Well, this was totally arbitrary. We started with this one because it looked reasonable, but there is no specific reason. We will see that, however, this choice does have an impact on our result. So conceptually, the system was like this. We had 2 syringes pumping the continuous flow and the dispersed flow on a microchannel, and here we placed a camera that could record the droplet trains over time. And then we elaborated these images to determine the length of the droplet and the distance between droplets. The pumps were this Harvard thing here, and the circuit is this one. As you can see, it's a small one with inlet and outlet pipes. And then the type of recording we got is like this. This is the image recorded by our camera that could only actually record a tiny fraction of our circuit. Then once collected this image, we needed to measure the droplet length and the distance between droplets. So how could we do that? Well, our first attempt was to place some bachelor student in front of the screen and try to count the number of droplets per minute, but they were not very happy, so they quit quite rapidly. So we said, well, maybe we should try something more professional. So we actually processed the images using some standard
image processing tools. First of all, we converted the image in a binary image. Then we performed a couple of filtering on the image to remove noise. And then we applied this connected components identification algorithm to extract the bubbles in our image. At this point, we could simply measure the size of these bubbles and the distances between any pair of bubbles. We could then plot this graph here, where we have the size of the droplets over time, generated over time, for the 4 different symbols that we consider. So each of these lines here with different color refers to the measured size of the droplets generated with a certain value of the dispersed flow rate, corresponding to the 4 different symbols. So ideally, if the droplets were perfectly deterministic in the droplet creation process were perfectly deterministic, we should have obtained some straight lines, right? But of course, the process is noisy. So on top of this average value, we have some variations due to physical phenomena. So we characterize the mean droplet length for each of these condition and the standard deviation, the error with respect to the mean. And we verified that actually the distribution of the error in terms of the size of the droplet and also the error of the interdistance between droplets, these errors are distributed like Gaussian random variable, at least as a first approximation. You know, when you don't know how to model something, you model it as a Gaussian or Poisson, depends. And therefore, we could plot these bell-shaped probability density functions for the 4 symbols, okay? So symbol 0, symbol 1, symbol 2, symbol 3. So receiving a symbol with a certain length, a length in this range, we could set the coding threshold in order to minimize the detection probability. And anytime we receive a droplet with a length in this range, we decide for symbol 1. And we drop the other symbols. Well, that's a classical, right? PAM receiving scheme. We can now estimate, well, something that should be noted before moving on is that the width of this Bell probability density distribution functions is not homogeneous. So the power of the error that affects the reception of a certain symbol depends on the symbol, right? So if we transmit symbol 0, we have a certain noise that affects this symbol that is different from the noise that affects symbol 3. So this is already something different from traditional communication systems. So we could characterize the error probability both when we use the length of the droplet as a carrier or the distance between droplets as a carrier. And performing some very basic math using our experimental results, we obtain in the setting that we use for our experiments these results, according to which you see the error probability when using the droplet length as a carrier was 10 to the minus 5, more or less. With the distance between droplets, we had a lower error around 10 to the minus 6. That is pretty low, right? And this is actually in good agreement with this plot here, because you can see that these bell shapes here are quite spaced apart. So it is quite difficult to confuse one symbol for another one. That's good. So apparently our communication system can be designed in order to have quite low error probability. Fine. What about the bit rate though? So here the question is a little bit more complex, because we need to account for different factors. First of all, we need to account for the time that is needed to generate a droplet and the space following that droplet before the next one. So this time, of course, depends on the length of the droplets, the distance between two droplets, and the speed at which the droplet will move in the channel once it enters the channel. So you put the math and you compute this value, and what you get is something in the order of 100 of milliseconds. So every droplet space pair takes approximately 100 of milliseconds to be created and inject it into the channel. It's a sort of symbol period, if you like. I call it chip period, referring to the spread spectrum type of modulation, because a single droplet space pair is probably not enough to decode your signal. You need, in order to increase the robustness of your system, you need to observe a train of droplets in space before being sure that the transmitted symbol is S0, S1, S2, or so on. How many of these droplet pairs do you need? Well, it depends on your design choices. So you can play with this parameter, KD, that tells you how many pairs you have to account in order to decide for one symbol or another one. So your symbol, the symbol period, will be given by the product of these two terms, the chip period and the number of droplets that you want to observe before taking your decision. One peculiarity of this system, however, is this term, tau d, depends on the symbol that you transmit. So once again, you have a communication system where the noise depends on the symbol that you transmit, and the symbol period does depend on the symbol that you transmit. Something a little bit unusual. This is not enough, though, because actually you can obtain this result if you keep your source rate, or better, if you keep transmitting the same symbol again and again. All right? So if you keep the volumetric flow rate of the dispersed fluid constant over time. So after a while, the system reaches a stable behavior, and you have this very regular train of droplets. But of course, if you want to communicate some information, you need to change the symbol that you transmit. Anytime you change the symbol, however, the droplet size and the droplet interdistance do not change instantaneously. They take some time to reach the new stable behavior. How long is this time? Well, it depends on the gap that you apply to the input. So if you change from symbol S0 to symbol S1, so you increase the volumetric flow rate of 0.5 microliter per minute, then the time to reach the new situation is, let's say, a few tenths of seconds. But if the gap is from S0 to S4, then you have to increase the volumetric flow rate of 2 microliters per minute. Then it takes something like 200 seconds. So you have a system where anytime you change the symbol that you transmit on the channel, it takes a different time to reach a new stable behavior. And of course, this time has to be accounted for when you compute the bit rate of this system. So as an intermediate step, what we tried to do was to model this transient behavior with, well, just, closing your eyes, you can model transient behavior with a very simple filter like this one, with an exponential impulsive response here. We characterized the parameter B of this system from our experimental measurements. So we try to change the volumetric flow rate from 3,000 to 2,000, 4,000 to 2,000, and all possible combinations. We experimentally characterized the parameter B. As you can see, the parameter B changes from case to case, but as a first approximation, we can assume it almost constant, with a value that is just the mean of the different values that we observed, that is this one. So using this parameter, we characterize the time it takes for the system to pass from one stable behavior with an input equal to 0.5 to a second stable behavior with an input that is 2 microliters per minute, assuming a certain tolerance margin proportional to the parameter alpha that we set to 5%. We made this computation for all the possible combinations of symbol switching. So from S0 to S0, of course, we don't spend any time because we are transmitting the same symbol. But if from S0 we transmit S1, then we spend something like 140 seconds. From S0 to S2, we spend more, and so on. So what you have is a system where, depending on the symbol that you transmit, you have different noise levels, you have different chip period, and you have different switching period. So the capacity of your system does not only depend on the symbols that you transmit, but also on the way these symbols alternate over time. So on the sequence of symbols that you transmit over the channel. That is, again, quite unusual. Well, this is what is written here, so let me skip it. So let's consider a few very basic cases. First case is where the source is maximum entropy. So all symbols have the same probability, and all transitions from one symbol to the next one have the same probability, 1/4. Okay, so in this case, each symbol will carry 2 bits. Sorry, this is the generic case, so we can define the source by means of this transition probability from symbol I to symbol j. From this transition probability, we can determine the steady-state distribution of the different symbols. And using these parameters, we can find the information carried by each symbol by just applying the definition of information, and the average time that it takes to transmit one symbol. This average time is given by the time to transmit the symbol plus the time to switch from the previous symbol H to the next symbol J. The ratio between these two quantities give you the bit rate of your source. So if you consider the case where everything is symmetric, you'll get, making the math, you'll get a bit rate of almost 1 bit per minute. Not that bad. 0.888 bits per minute. This is not very, super fast, but it's something. But the weird thing is that if you consider a simpler system and you just drop these 2 states, you just consider a 2-symbol PAM type of modulation like this, your bit rate increases to 0.984. If you go back to the original system, but you do not allow all transitions to occur with the same probability, but basically what you do is coding your source. So introducing some correlation between the different symbols that you transmit over the channel, and in particular trying to avoid switching from one symbol to 2 symbols or more symbols ahead. So try to somehow limit the switches only to adjacent symbols. What you get, this was just a random matrix that I wrote during the flight here, all right? So nothing really thought upon. So what we obtain is a throughput that is even larger than 1 bit per minute, 1.5, let's say, bit per minute. Okay, so what is the conclusion? The conclusion is that transmitting bits using microfluidic systems is possible, but the problems that we face are completely different to what we are used to. So we have a system where the bit rate depends on a number of factors. It depends on the symbols that we decide to transmit. It depends on the sequence of symbols over the channel, so on the calling rate. All right? And therefore, you can actually spend a lot of time to investigate this kind of systems. So what can we do next? Well, we can first of all try to find the optimal setting of the parameters in order to maximize the bit rate of a PAM modulation on these kind of systems. We can investigate more sophisticated modulations, combining length and distance, maybe using the distance as a sort of, or the length as a sort of redundancy type of code, so to increase the robustness. We can use other circuits to dynamically change the droplet interdistance rather than creating a train of droplets of the same size. With a T-junction, we can think of more complex systems to have a more rapid modulation of our carrier signal. We can consider other performance indexes, delay, energy consumption, but most of all, we can try to figure out what might be a possible application of this kind of technology. I've been thinking about that for a while, but I don't have any answer, because we have a system that can transmit, if we are lucky, 2 bits per minute, maybe 3 if you are very good, 3 bits per minute over a distance of a few micrometers. That might not be the, the ideal communication system. But maybe, well, my hope, first of all, I did this kind of research because it was interesting, it was cool. So sometimes you have to enjoy life, right? So you do something even without a specific target, even though we are supposed to do the opposite, but don't tell anybody. And second, there is always the possibility that, the type of reasoning that this kind of study triggers in your mind might find an application in other fields. So for the moment, what we tried to do was to apply what we know in this microfluidic domain, but it's also possible that what we learn from the microfluidic domain can be applied in more traditional fields. You never know. And finally, if you are wondering whether you can publish these kind of things, well, the answer is yes. It's not super easy, but you can find a way to publish these results, mainly on conferences, but we also have a couple of journal papers. And that's it. So if you have any questions, I'd be glad to answer. Thank you.
Thank you, Andrea, for this interesting talk. Any questions?
I was wondering whether you could use the error from one symbol to the next as another source of information to increase the overall information transfer of the system.
Well, that's an interesting question. So you're saying, if I understand correctly what you say, is that if it is true that the power of your error depends on the symbol that you transmit, it is actually delivering, carrying some information itself.
Precisely.
That's correct. That's good. That's correct. As a matter of fact, what you know, this is a very preliminary type of study, but the next step might be also to investigate the transient behavior. At the moment, what I assume is that you have to wait for the end of this transient behavior before deciding the next symbol, but this is not mandatory. You can just try to measure the speed at which the length of your droplets are changing over time, and this also carries some information. But future work.
I might want to add something to that. So if you look at gene expression in cells, most of the time your genes are either absent or they're present at certain concentrations, and it's such a way that a cell has acquired the ability to, if it wants to switch rapidly, it will not start from no signal at all and then switch to complete signal. It will be like there, just below the area, and then it quickly exceeds the threshold, and then you actually have your signal. So in my opinion, like you were mentioning about the transient, actually you can exploit this because it's the proximity to this where you really have the signal actually might make a difference. Not whether you can really separate them. Sure. So my question when you showed the four Gaussians, but I think you more or less said it when you were talking about the mathematics. I mean, you have a very low error there, 10 to the power minus 7, 10 to the power minus 5. So I was wondering, how much can they overlap so that you can still have a discernible signal?
This is an excellent question. As a matter of fact, something that I didn't mention, but it's written in the slides, is this thing here. You can play with two parameters. One is alpha, and the other one is AD. So alpha is this thing here. Is the tolerance that you accept before saying that the system has reached the next state. So if you increase alpha, you're saying that you basically assume that the transmitted symbol has been changed, even if the length of the droplets has not reached its final value. So doing that, if you increase alpha, you speed up the switching between symbols, but of course you reduce the distance between these Bell PDFs.
Yes.
So after a while, they will overlap. So you have a trade-off here, because you can have these bells overlapping, so the probability of error will be increased, but the switching time between one symbol and the other one will be decreased. So what can you do? You can somehow speed up the switching between symbols, but then wait for more symbols before deciding, more droplets before deciding which symbol has been transmitted. So you have this sort of trade-off.
And you can address, because now you consider every symbol to be independent, but like in language,
all right,
or like in DNA, or like in molecules, is a sequence of characters that actually determines the entire thing.
All right, okay.
So you can actually say, okay, when I view a 1 followed by a 2, or a 1 followed by a 3, or this is different meaning than 1 followed by a 4, and so on. They can actually.
I do like this approach. All right, nice. Thank you.
Yep.
Good suggestion.
Thank you. Just a very short nano question. What are the needs at the receiver end? What did you need for demodulation for length estimation? Is it an energy detection like receiver?
That's an excellent question.
Is it an integrative?
Yeah, excellent question. We didn't consider explicitly the receiver, that however must be designed properly. So for the moment, what we assume now is to have a sort of optical detector that is able to measure the size of the droplets. You can build it either using a camera that is kind of expensive though, or maybe with a simple LED and a light sensor on the opposite side that samples very quickly what happens in the channel, and when you have a droplet that basically obstructs the line of sight, you know that there is something passing by. If you sample rapidly enough, you can measure the size of the droplet with a certain granularity. So this might be a possible receiver for this kind of communication system.
And then a very final devil's advocate question. is this modulation or this modulation scheme energy efficient? How do we define energy here? Is it the amount of liquid? Is it the energy you need to pump?
Excellent questions, but if you go to my final slide, is one of the things that we left for future work, I can say. So the investigation of the energy efficiency of this system is something. Well, it's something that still has to be done. You see, energy consumption here. As a first, you know, my feeling is that these kind of systems are not energy efficient at all. Because, well, to power your pumps, you need to spend some energy. And the bit rate that you get is beats per minute. So I don't expect these kind of systems to be very efficient. So what might be the advantage of this system? I don't know. This is the last point here. I don't know yet. But maybe you can find an application where, as we were discussing during the lunch break, an application where standard communication systems cannot be applied, while this kind of system might be the only solution that you have. So in that case,
Things are very opportunistic, built in there.
yeah, maybe. Or perhaps some of these concepts, but I'm not sure about that, might be reapplied on acoustic communication for underwater type of communication. Even though, of course, the environment is completely different, but maybe some concept can be also applied there. All right. Oh.
So you have shown us these Gaussian bell curves, and somehow it seemed that those curves that were closer together were also narrower. So why is this, or is this kind of luck?
No, sorry, I didn't get this.
So we have seen these bell curves,
Yeah?
and then some of them were closer together, and those that were closer together were also thinner
All right.
or higher. Yes.
Here you say.
Yes. So is this luck, or why is this?
Well, this is simply the way in which we obtain the results. These are experimental results. All right. So the distance between these bell-shaped PDF is given by our initial choice of increasing the volumetric flow rate with discrete steps of 0.5 microliters. But if you increase the volumetric flow rate of a constant step, the length of your droplet is not increased by a constant value. Sorry, I have to go back here. You see? So if you add a delta here, what you get in terms of length is proportional to delta, but not linearly proportional. So if you have 2 times delta, you don't get LD plus 2 times the increment that you get with a single delta. You get my point? So since we use this increment here, so we increase with a constant step the initial volumetric flow rate, what we obtain are 4 distances whose interdistance, however, the difference between LD1 and LD0 is probably larger than the distance between LD2 and LD1 and so on. So we have this effect that you noticed. You have a very good eye, by the way, according to which the bells are not, you can see also from here, you see, the distance between these 2 symbols is different from the distance with these other 2 symbols.
Yes, but interestingly, we also have this correlation that those where the distance is smaller.
Kind of,
yes.
Right, I can't explain this. Yeah, probably because the error in the droplet formation process depends on the size of the droplet. Mm-hmm. So, since these droplets are, if not wrong, are shorter than these ones, you also have this correlation between the size of the droplet and the noise that affects the droplet generation process. So this is just by chance though. So if you move this droplet closer to this other one, the shape of this one will remain the same, of course, right? Yeah.
Okay.
Since I think we already run out of time, we move on to the next. Oh, is this a short question?
There are a number of questions, but
Yeah, I think.
well, I stay here till tomorrow. So.
Yeah, definitely.
Oh, I'm so happy. It's the first time that I see some questions apart from apart from what's the use of this kind of technology. So thanks a lot. Thank you.
Yeah, not working? No. Okay. Yeah, my talk will closely follow the first talk of Giacomo and is definitely inspired by the previous talkers. It is the first attempt to introduce some kind of design automation for this discrete multifluidic area. But it's important to know that for the electrowetting-based discrete multifluidics, design automation is a well-established research track. I think they do it since more than 10 years. And what we tried to use this method for this discrete channel-based microfluidics. To shortly sum up what we have learned so far, so droplets flow along the channel or the path with the lowest hydrodynamic resistance, and droplets increase the resistance if they flow in the channel. And exploiting this fact, a so-called header droplet can steer some payload droplet, which includes the chemical or biological sample through a series of junctions to some desired module where some chemical reaction can take place. To illustrate this, you have a payload and a header droplet, and the information is encoded in a distance. They arrive at the junction. The header goes to the lower channel, which has smaller length and therefore the lower hydrodynamic resistance. It increases the resistance and the payload then goes up. So this is the basic principle in this microfluidic network. Well, having this concept, we thought about how to extend the concept which introduced by Professor Zanella and Professor Morabito. And we first came up, okay, there is no concept how we can process multiple modules one after another. So in current concepts, you go to one module, go back to the pump, and then you can execute another operation in a ring network. So injecting this payload, again at the source, is some complex task, and you may destroy the payload. So one principle which we came up and will present in 2 weeks at the ICC is we introduce some droplet sorter here, and the basic principle is why not use multiple header instead of only one header. And again, the information is encoded in the distance, and the concept here is for each module you want to skip, you insert a header droplet. So it's very efficiently if you want to execute many of these modules. The problem is you have to use these header droplets also after a module. So you have, for example, 3 header droplets, and one header droplet is responsible for skipping the first module, and you need the others for skipping other modules. So how can you pass such header droplets over this module? And this is done by some droplet sorter, and therefore we introduce different sizes for header and payload. And the interesting thing here is this droplet sorter, because we all want to build passive microfluidics, that's a passive droplet sorter. So also no active elements are in there. So the 2 basic principles, introducing multiple headers and passing the header droplet by the module by having different sizes. I think I can really quickly go over this. I just want to mention it, how you can simulate these things. Giacomo already mentioned you can simulate microfluidic networks using COMSOL or OpenFORM. The problem is you can really precise model simple T-junctions, but when you go to more complex, or if you have 2, 3, or 5, or even a network, it's hardly possible to do it with such simulators. So they came up, as a group of Professor Zanella came up with a MATLAB-based simulator which uses this equivalence between microfluidics and electrical circuits and model the microfluidic network as time-varying electrical circuit. Yeah, it has some drawbacks. It only describes the speed and the trajectory through the network, so it does not describe any deformation of the droplet or something. But for our purpose, that's enough. So we just want to how fast it goes and where it goes. The main advantage, it has a significantly less computation time, which is especially important when the network scales up. And it, for the first time, enables real simulation of such microfluidic networks. That's also very important. Yeah, and this thing looks like this, for example. Hopefully it works. This is an example of a ring network with the concept proposed above. So you have three modules. The payload is the blue one, and you want to skip module 1 and 2, so the blue one, which comes at latest, should only execute the third module. And what you see here, the green one only here. So the yellow one was inserted first, is responsible that it skips this model, and the yellow one was responsible for the next one. So if someone is interested, I think we can look at this video at a break. The main point of my talk is we want to introduce design automation. So we asked ourselves, we have a set of laboratory experiments. This is somehow defined. We have, each experiment requires certain operations, splitting, mixing, fusion, all of the stuff. You have also various physical constraints. No loops, maybe only bifurcation with two successor channels. You can define it by what you like. And we would like to have some design objectives. So we want to design it to have a minimum number of modules, a minimum number of channels, a minimum number of contamination, so how often a droplet passes a channel, does it influence somehow the experiment. This we also want to define somehow. And the question is there an architecture, so meaning a microfluidic network, which fulfill all these requirements? And what you can do, using some Boolean satisfiability solvers from computer science. So we transfer this initial design problem in some kind of decision problem. So we start with a global network with all connections and introducing some constraints, and this results in some architecture. The problem then is, it's not all about architecture, because you need the corresponding droplet sequences. So the next thing we thought about, okay, how do we automatically design the according droplet sequences, meaning the sequence with one payload droplet and multiple header droplets in front of. And as an example, we have an architecture. So our starting point is you have an architecture from the previous procedure, and we're asking ourselves, is there an appropriate sequence which can execute, in our case, these three experiments. So we don't think about any header droplets. Okay, you can see, okay, it's easily, here you have M1, M3, M4, which would be experiment 1. Then experiment 2 is M2, M3, M4. And this one, M2, M3, could also be somehow executed from a very intuitive point. But then remember, okay, we need header droplets to steer the droplet inside this microfluidic network. And what you can see here, this double arrow is the default direction, meaning this is somehow the channel with the lower hydrodynamic resistance, either with a bypass channel or with wider width or something. And this is the flow direction. And what is very interesting, to conduct the first experiment, no header droplet is needed. It simply goes along the main directions. If you want to conduct the second experiment, you just have to insert one header droplet in advance. then it goes this direction. And the really bad news, the third experiment you cannot conduct with this architecture. Without going into details, two problems can occur. One problem could be that some droplet collision occurs here because of different channel lengths and speeds. Or if no collision occurs here, then it might or it will be that the droplet, the payload droplet, takes this path. So having this architecture, it's not possible to conduct all these three experiments. What to do now? We want an automatic design solution for that, and we again formulate some design decision problem. It's a similar procedure. Is there at least one droplet sequence for each experiment? We only need one. That it can be executed. So for each of the three experiments in our previous example, exists a droplet sequence. Yeah, again, you can formulate this with these SAT solvers, and you can do it in some iterative way. So you can say, I make an architecture, see if there exists a sequence, then putting this information back to the architecture procedure so you can make some kind of iterative procedure. And in future work, for sure, there must be some joint approach. Yeah, so this was our first attempt to somehow bring design automation to this microfluidic network. What is required, one remark, for this design optimization is we cannot use COMSOL simulation, we cannot use this event-based time varying simulator. We have introduced another abstraction level in order to make this kind of decision problem, in order to solve it. For sure, it's not that accurate as the other models, but it's, from our perspective, for a moment, the only way to do some kind of optimization. But, yeah. So our contributions, to briefly sum it up: droplet forwarding, first work on automatic solutions. So what are, from our perspective, beside the why question, what is need? What you definitely need is somehow models for this, I call it modules. Some resistance model or something, capacitance model, somehow to get it more practical. So how, when you talk about the splitting device, how can you model this? I mentioned this joint design. I think this should be the ultimate goal of this. Use cases, Giacomo also mentioned it. And one of the, I think, main things is you have to somehow experimentally verify the things. Droplet on demand, maybe this also can help in your case, and for deep engineering. Yeah, that is from my side. Thank you.
Thanks a lot. Very interesting. At first, I thought from the title that design automation was something very bold and therefore interesting. To my humble understanding, what you did, it's an architecture design optimization or architecture design space exploration, not in quotes EDA, not yet. Perhaps a first step. Now, two reflections. If you would ever like to go from communications to a complex network, a complex microfluidic network, how and when would you deal with multi-scale, multiple domains, heterogeneity of the networks, and how would you include that in your simulation?
What do you mean, for example, with heterogeneity?
Heterogeneity in the different models of the architecture. Since you started talking about EDA, I thought about complex systems on chip, where you do have heterogeneity in the networks on chip and etc.
Okay, yeah. So this would be then maybe not the next, but after the next step.
Then why don't we talk about a first step? Do you consider sort of a multi-physics simulation, a co-simulation between COMSOL and the event-like simulator you propose? What would that imply?
Is this, let's call it discrete simulator, where we ran out of this. We verified with this time varying simulator, and this time varying simulator was verified by COMSOL. So we did some verification.
It's vertically integrated. Yeah. Okay. Yeah, thanks a lot.
We might just take the questions offline, just to carry on for the last speaker. Yeah. Okay.
Yeah, we carry on because we are running quite out of time. So our next speaker is Ryan Silver from Boston University. So I track it. Take your time, don't hurry.
Oh, that's cool. I talk fast anyway, so.
Don't have to talk fast.
Appreciate that. Appreciate that. Okay. Yeah, here. Beautiful. Beautiful, beautiful.
So I think we are now going away from the droplets. We are now going to the continuous flow.
Droplets are so hot in the streets. We'll have a little bit of droplets in there for you, but yes, we are going to continuous flow.
Yeah,
and let's talk electronic design automation for a second. Okay. Let's do it. Okay. Good afternoon, everybody. My name's Ryan Silva. I'm from Boston University. I'm a graduate researcher, and I want to tell you guys about a really cool specification to device tool that we dreamed up here in the lab at Boston University in conjunction with a boatload of partners. So hopefully this afternoon's tech session has convinced you guys that microfluidics are awesome. Oh, am I shouting? I do that all the time. My wife tells me to shut up. It's fine. Microfluidics are awesome. I mean, they can reduce our consumables, they can give us high sensitivity, all in an automated fashion with better resolution, scalability to the moon and back with ultra high throughput. Wow, phenomenal. So one would expect, in light of all of these benefits, to walk into any biology, chemistry, or physics lab and trip over the mounds of lab-on-a-chip devices that everybody's using, right? Well, however, one's experience sort of tells us that microfluidics are very much the exception rather than the norm. Now, I believe, in particular, to actively controlled continuous flow microfluidics, this is a result of a very high barrier to entry into the field. It's relegated to pretty much experts only, to microfluidics labs. Those are the only ones who really do microfluidics. Papers on microfluidics tend to focus more on the device rather than the capability unlocked by the device, which is fine, but what this results in is really a lack of modular components and an inability to stitch these components together into more larger functional subsystems. So in that regard, you might be thinking, well, hey, Ryan, there's some very good tools out there that have different mechanisms for controlling fluid flow, like electrowetting, like surface acoustic waves. Why are you focusing on continuous flow? We're particularly interested in continuous flow primarily because of its ability to scale. We can make, transport, and analyze tens of thousands of cell-free reactions encapsulated in droplets in a matter of minutes. We've proven our ability to, let's say, you draw 10 milliliters of blood from a sepsis patient, and you want to figure out what bacteria they're sick with and what antibiotics that bacteria is particularly susceptible to. However, the larger blood components sort of confound the assay. We'll talk more about this at the end of the study. I'm really excited about this. Well, using acoustophoresis in a continuous flow device, we can separate those large blood cells relatively easily in a matter of minutes. 10 milliliters of blood. We're talking about 10 to the first cells per milliliter, so not a lot of bacteria and relatively a lot of blood, but again, I'll talk more about that. So why continuous flow? So now let's talk for a second about the 3 levels of design automation. There are some very good tools that exist right now that will allow you to specify some high-level behavior, some high-level function like do PCR, go, and that will be synthesized down into a microfluidic device, and it'll give you this device and say, here you go. But that's where it leaves you, unfortunately. It leaves you with a microfluidic design. And if you're coming from a lab with 0 microfluidic infrastructure, you're really left with no recourse on how to actually act on that device, unfortunately. So what I set out to do, particularly in this framework, is fill in this bottom section. How do we actually build a device, but do it in the easiest, cheapest possible way? And there are trade-offs. For a small cost and trade-offs, it's actually a pretty big cost and trade-offs, but we'll talk about that later. How do we actually do this? Well, the idea is what we want to do is consume a device layout that you're given in this design automation sequence, spit out a physical device, but not only that, have a physical device in your hand that you can actually introduce fluids and control those fluids in a mechanism and in an environment that consumes a control sequence generated by your design tool, all using microfluidic infrastructure that you build yourself. You can go from zero microfluidic infrastructure to a continuous flow setup in your lab for roughly around $3,500 US. So not too bad, and we'll talk about what you have to give up in order to get that here in a moment. And it's this build layer that I'm calling Maker Fluidics. So underneath this whole EDA chain, there's a lot going on. There is a lot going on. We can talk about it, but if you want to get involved with this particular chain, we present everything to you in a user interface that we call Neptune. Again, I'll go over that towards the end of the talk, but you don't need to worry about what goes on under the hood unless you're really interested, and we hope you're really interested. But if you just want to use the tool, we've packaged it up in such a way that any lab can figure out how to use it. Now, I told you guys that I made a microfluidics fabrication framework, and it'd be really inappropriate for me to go on without actually defining what that is. I consider, and the field considers, a microfluidic fabrication framework to be the answer to 3 questions. How do you pattern your geometries? What a geometry is are like your channels, your valves, your reaction chambers, the thing that make your microfluidic chip. How do you get those into a substrate? Then once you have these 2 layers, your flow layer through which your fluid flows, and your control layer responsible for your valving and actuation of that fluid, how do you bond those things or seal those things such that you can introduce fluids without making a mess? So once you can seal your chip, how do you actually introduce fluids and control your chip in a way that actually makes it work in the way you want it to? So if you answer those 3 questions, you have made a microfluidics fabrication framework. So let me tell you about a traditional microfluidics fabrication framework. Pretty much the state of the art right now, the way most people are designing microfluidics. Well, your design is given to you probably on the line. Your design is more than likely a vector graphics file generated in Adobe Illustrator. This is still the state of the art right now, to go into Adobe Illustrator and click and draw everything by hand. And then you print out this design literally on a transparency, the same type of transparency you probably used in grade school in conjunction with an overhead projector. Except now you give it the fancy name, a photomask. And you take it upstairs to your clean room, because you obviously have a clean room, right? And you take your silicon wafer, you spin on some photoresist, you put it in your mask aligner, because you have a mask aligner. And you put it in your mask aligner, blast it with some UV, and out pops your mold. You take a silicon elastomer, it's called PDMS. You can actually go to a hardware store and buy it. We get ours from Amazon. Pour that on top of your mold. Now you've got your flow and control layer, and you take it over to a microscope. And now you have to really be careful when you align your 2 layers, because any misalignment, even a little bit, don't drink coffee, make sure you get a good night's sleep. Any misalignment, when you put it in the plasma bonder, which is an irreversible surface treatment, means that your chip is useless and you have to start over. But with this whole setup, you can achieve fantastic resolution. We're talking the nanometer scale in terms of the architectures and the geometries you can make. Wow, that's fantastic. However, the equipment cost is staggering just to get started, and that's just in equipment, not necessarily the facilities to house that equipment, like a clean room, and the training and human capital required to actually run the equipment. You're going to spend at least an entire day making a batch of chips if you're really good. If you're not so good, it could take you upwards of a week or a month, so I'll tell you. And at the end of the day, it is a human in the lab doing this the whole time. So you can see why there's a relatively high barrier to entry, and maybe why not a lot of labs are using microfluidics. So what you're going to give up if you use Maker Fluidics? Well, what I have here is the traditional photolithographic way of fabricating chips here on the left, and I have the Maker Fluidics method on the right. If you're willing to give up the nanometer scale, if you're willing to give up irreversible bonding, then we can get the job done for you for roughly an order of magnitude less in cost, time, and take the human out of the loop. So let me tell you how I do that, starting by answering the first question: how do we pattern our geometries? I heard a lot about 3D printing, and that's awesome. I'm totally excited about additive manufacturing. We chose a different route. We chose subtractive manufacturing, computer numerical controlled mills. Essentially, you can imagine a drill bit that spins around and removes material that way. Rather than in 3D printing, it's the same thing except you're squirting out plastic. We chose this mostly because of the fact that you can use any type of thermoplastic substrate or even metals or curable wax we've tried. It's actually quite useful. But what I want to focus on is all you have to do is press a button and click cut. You import your design and click cut, and you sit back and watch. So it's a very user-friendly, it's a very quick mechanism for ablating some substrate from your microfluidic device and making it into your microfluidic device. Now, there's been a lot of advancements in computer numerical control micromilling over the last even 3 years, where the form factor has shrunk down to the point where we fit our CNC mill onto our bench, like our wet lab bench. It sits right there, it's not obstructive, it's relatively small, and I'll bring up the form factor here in a moment. And the price of the micromill was $2,500 US. We use other mill by the other machine company out of Berkeley, California. Unfortunately, they do not ship internationally, so we have tested a Carbide 3D product called the Nomad 883 that you can buy right now, and they ship internationally, except the form factor is a little bit larger. In both of these mills, the performance is about the same. Performance is about the same. And with this, you can use it to make microfluidics in just about any thermoplastic substrate. I've used polystyrene and polycarbonate significantly. You can autoclave polycarbonate, which is really nice. Acrylic works as well. Our surface roughness has never been an issue, even when we're dealing with cells sticking to walls, which is fine. Which isn't fine, but with the surface roughness, we don't see a problem there. But once you pay the overhead for the mill, we can get you microfluidics in less than an hour for just the cost of the plastic. So we're really excited about that. So that's the answer to the first question. How do we pattern our layers? We use a CNC micromill. Now, once we have our 2 layers, our flow layer, again, through which our fluid flows, and our control layer that's responsible for our valving, because we do use active control mechanisms, how do we bond these 2 together? Well, we use that silicon elastomer PDMS that, again, we source through Amazon, but you can buy it in any hardware store because it's used to encapsulate a lot of outdoor things such as solar panels or anything else that requires transparency or translucency that needs to be outdoors or weatherproof. So we literally bake our PDMS in a toaster oven. If you don't have a toaster oven, it cures at room temperature overnight. So not a big deal. But again, it's just a monolithic slab. There's no mold. It's just a blank piece of PDMS. And we use the inherent attraction of a thermoplastic and PDMS, just van der Waals force, to secure the bond together and create a pneumatic and fluidic seal. It's very simple. Now, I told you we use active valving. So how do we actually do that? We use a valve that was, wow, you can't see that, poor Dr. Grover. Dr. William Grover out of UC Irvine pioneered this type of a valve about a decade ago, in fact. All it is a discontinuity in the flow layer and a corresponding cavity in the control layer. If there's no vacuum present in the cavity, well, your fluid has nowhere to go. It hits that bump, it stops. But if you introduce a vacuum into the control layer, well, your fluid hops over the bump and you're good to go. So now you're sitting there thinking, well, hold on, Ryan. You told me no microfluidic infrastructure, and you're talking about pneumatic valving. Hold on, pal. Well, the way we achieve pneumatics, the way we introduce pneumatics into our chip is with cheap open source 3D printable parts. And we've been through every manner of design for a cheap syringe pump. And I'll tell you, we even dabbled in centrifugal microfluidics. And we've settled on this design that's really only 1, 2, 3 parts in a servo. And it's customizable, so you can pick whatever type of syringe, whatever size, however large or strength, which we run into when our designs scale to the order of hundreds of valves. We need a relatively strong pump. And, well, wait a minute. I mean, like, this is confusing. This is great, but I have no idea how to build this. I've never worked with electronics before. I'm sure we all have, but I'm just saying. These are the questions I get, which is fine. I've never worked with electronics before. I don't know which syringe to pick. Well, built into Neptune, remember, Neptune is the mechanism by which you designed your chip in the first place. So it knows how big your chip is, and it can recommend a servo-syringe combination and tell you where to buy it. Right now, unfortunately, we're using Amazon.com, which sources also from Amazon.co.uk. I don't know what the Irish equivalent is. I don't know what the other European equivalents are, but that's a significant limitation that we're trying to work on. But it will add these to an Amazon cart for you. So we're trying to expand that out to other commercial retail outlets. But it will recommend some type of servo-syringe combination, download all the 3D printing files you need, and give you step-by-step instructions on how to actually assemble your syringe pump. So great. And now what you have in your browser is a means to actually interact with and control your chips. So I'll just fast forward here. Cool, you can interact with buttons, connect to an Arduino, which is all built into the instructions on how to actually assemble this thing. And now you can watch your fluid go. Look, red fluid flows through, now blue fluid. How cute. Great. How do you actually apply this thing? What is this thing good for? This seems like a toy, you know, very cute fabrication framework. It's probably not useful. You used it to move colored liquids around. Fantastic. Right, yeah, well done, Ryan. Good. Well, the way we proved the usefulness of our fabrication framework is we tried to do two things. The first thing that we try to do is make a relatively complex circuit. We're talking scaling to hundreds to thousands of components. So can we make and control a complex microfluidic chip? And then the second thing we try to do is make a biologically relevant chip, something that industry is interested in. And so we managed to accomplish both. But let's talk about the first thing, a complex chip. I'm at 14 minutes right now, so I'll talk fast. So what we did was we made a primitive that will allow for arbitrary routing across any continuous flow microfluidic network. So what that means is that you can have n inputs coming into your microfluidic chip and n outputs coming out of your microfluidic chip, and you can route any of the n inputs to any of the n outputs without interrupting flow in any of the subsequent channels. So we just made a primitive, we scaled it, we built it, we boiled it down into just a graph traversal problem, which as EDA people, we love traversing graphs. We love all manners of coloring and traversing graphs. So it's great, it's therapeutic to actually watch this video. I don't know where my mouse is, or else I would fast forward it. But we go through every single iteration of red, green, blue, all the different permutations or combinations thereof. We published this research in Lab on a Chip. So the community's actually, they sound like they're interested in this kind of thing, which is great. But now let's talk about the biologically relevant case. We partnered with the Charles Stark Draper Lab in Cambridge, Cambridge, Massachusetts. And they had a problem where they're trying to develop a point-of-care device for identification and antibiotic susceptibility testing in sepsis patients. Right now, if you're sick, they draw your blood, they send it off to a lab. Hopefully you're still alive in a week when the results come back. In the meantime, you get a broad spectrum antibiotic, and there are a lot of problems with that. So what they wanted to do was determine what bug you're sick with at the point of care. However, the problem has always been the larger blood components confound the assay. So what we do is we use acoustophoresis, which is basically shaking the chip up and down really, really quickly using a piezoelectric transducer. We're talking on the order of hundreds of kilohertz here. And what that does is it creates pressure gradients inside of the channel. And these large blood components are more sensitive to higher pressures, and thus they get pushed to the middle. Red blood cells and white blood cells are much bigger than the fluorescent bacteria you see here. So the blood cells get pushed to the middle, and you get a nice, clean, pure bacterial sample here on the sides. We've also done this to enrich lymphocytes for engineering T cells. Pretty fun stuff. If you want to get involved, you can point your browser right now to 3DMicrofluidics.org and take a look at our fun little point-and-click drag tool that will allow you to design just some microfluidics right now. That's in a public alpha. We know there are bugs. And if you want to get involved in the development or the deployment of Neptune, just let me know, and I'll get you on the list, and we can walk you through how to set up and use Neptune, and all it'll cost you, or if you have access to it, is a miniature CNC micromill for about $3,000 US. Hey, I'm done. I didn't talk as fast as I wanted to. I'm at 18 minutes, I'm sorry. But we also do droplets, so there you go. All right, I'm open to questions. Thank you.
Thank you for this really exciting talk. Any questions? I think 2 questions.
You gotta be kidding me. Beautiful. Wow.
Again, a naive question. Feedback loops. Would that, because seems all very linear to me, and a lot of things are done by positive and negative control in other kind of biological systems. So how would this work in the context of these microfluidic chips? And actually, can that work in the context of these microfluidic chips?
So if I understand your question, you're talking about closing the loop regarding, I guess, analyzing what's going on the chip? Or?
No, it's the fluids that control the flow of themselves. So if instead of having it simply going to an output, actually bring it back into the system and actually have these things like positive feedback control or negative feedback control in your system.
That's really interesting. What we're trying to integrate right now, and you can see that in the video, is some kind of closed feedback loop where you can figure out using a camera what's going on inside of your chip, and that implies the existence of some kind of loop or some kind of sorting device. Right now, we're not quite there yet where the fluids can sort of control themselves. It would be amazing if we could get there as far as, I guess what that would imply is a truly automated device, which is ultimately the dream, I think, of every microfluidic architecture designer. So that's a really good point and a really good question. Appreciate that.
May I ask yet another naive question then?
I'll be right back.
I think that your implementation approach is really valuable, and I particularly liked what seemed to be like an FPGA for microfluidic networks. What I don't understand, out of ignorance, how can you ever talk about a modular approach of systems of hundreds of devices if you don't decouple the different functionalities? Giacomo was talking about the strong interplay between the different parts. How can you ever think about that?
I mean, it's a great question, and just to leverage your example of FPGAs inherently relate to standard cell libraries and ASICs. So I would argue that, say, an EDA tool doesn't necessarily know what an AND gate is, and there are a million different types of AND gates in a standard cell. It doesn't necessarily know what the trace width is such and the crosstalk is such. It just knows that there are certain design rules, and it's primitive based is what I'm trying to get at. We know that primitives provide some functionality, and you can tweak that functionality by adjusting parameters. So that is the approach we take in designing, or an automated approach to designing our chip, is we know that there are primitives, and we know those primitives have parameters, and then you can go about tweaking those parameters, and there are one or two ways to do this. And microfluidics people love to model things. They love to model things to death, and we take the opposite approach. We say, well, instead of spending a month modeling things, I think we learn a lot more by actually going out and building something quickly. That's why I love the 3D printed approach. That's why I love the CNC approach, because it's quick to get a device in your hands and test it.
Now, in FPGA, you have inherently decoupling because you just connect unloaded digital gates. In very complex systems on chip, IP blocks are intrinsically decoupled. Here, there is a fundamental coupling between different parts. Are you saying that you tweak the parameters to get decoupling between the different parts of your microfluidic network? And if you do, are you losing performance?
We definitely lose performance. That much is conceded. To answer your question, yes. So even in an FPGA, you have primitives. If they're lookup tables, all you have to do is reprogram a lookup table and then modify the connections to such lookup table. For a microfluidic, unfortunately, it's a little more application specific. So you can't necessarily turn a droplet generator into a mixer. I guess you could. That was a bad example, but you couldn't necessarily, you get what I mean.
Can you think about buffers to decouple different parts of microfluidic buffers?
Oh, now that's interesting.
Coffee break then. Thanks a lot. And
that would work.
Very good work.
Thanks again for this really cool talk. Since we're already very late, we will skip the final talk of Professor Leo and try to fill it in tomorrow's program.
Let's do a break, because otherwise we will skip the next section.
Yeah, now we make break.
I think it's
I'm
one of the organizers, sorry.
So now.
Constrain on the general program. Let's go for
Yeah, let's go for a break. Okay, thanks.